Alright, welcome back. This is lecture 11, we're almost there, of the series Physics 1. So in the last lecture we talked about all sorts of new angular variables that we had dealt with. Angular just means that we are now looking at things as revolving, right? Revolutions, things in motion in a circle rather than just straight lines, but it's that motion of rotating. And we made it up through energy. Of course, there's still another character that we haven't talked about yet, and that is the momentum. So the angular momentum and how that relates to linear momentum, which we had already discussed in lecture 9. So let's hop on in. For torque, taking one step back here, for torque, it actually was two vectors that were multiplied together, but there is a slight difference to what it was before when we had looked at two vectors multiplying together. So that was, we had previously looked at work, where the two vectors were comparative with a cosine function. In this angular representation of it, they're related with a sine function. So it's not quite the same. We still have two vectors that are being multiplied, but this time it's with a sinusoidal function. So it's different than it was before. It's not a dot product. It's called a cross product. Which means, of course, that the maximum occurs at 90 degrees and is 0 when there are 0 degrees. So cross products take a bit more work to figure out. That's why I kind of waited a little bit on the angular momentum in order to shift, because it is a little bit more math. This is, again, linear algebra, so it's just straight up algebra course ready for this. And we see that if we have torque, which is again our angular force, we need to have an R times F. That's our normal routine, is to multiply it with an R in front. But these needed to be at sine theta. Okay, to get the sine theta to factor into this multiplication, it is known as a cross product. So this is not, it is multiplication, but don't assume this to be just a value for R times a value of F. This is a cross. You have two vectors crossing each other. Now the normal mathematical route of it is to say that the cross product C is equal to any vector A crossed with vector B. That, in turn, is equal then to a magnitude, whatever C's magnitude is equal to the magnitude of A and B and the sine of theta between them. That's exactly what we see when we look at torque. The magnitude of torque is magnitude of R, magnitude of F, sine theta. So this is exactly the same. So this is the mathematical cross product. Now, how we do a cross product? There are a couple of different ways that you can do a cross product with two vectors. Everybody teaches it just a little bit differently, and there's even a formula for how to figure it out. So what I'm going to do here is I'll show you in the videos following this. This will be a short lecture, mainly videos of whiteboard practice problems, and I will show you how I do it. If you choose to do it that way, that's totally fine. You can do it that way. If you learned another way, use that way. Okay, it won't matter to me at all, but as long as it's correct. You will see that when you take a vector A crossed with a vector B, you see that only the 90 degree components are multiplied each other. So here we have a y component of A and a z component of B. These two are multiplied together. Then we also have a z component of A and a y component of B. The minus sign in here, you'll see why when we do it out on the board, why it comes up as a minus sign. But you'll notice that, yeah, all of these components are 90 degrees apart. X and Z, X and Z, X and Y, X and Y. There's no like components because, again, sine of 0 is going to give you 0. You'll notice here too that all of the I hat, or what we would consider the X direction, doesn't pertain to any of the X direction components of these vectors. Same with the Y. There is no Y component in the Y component, which is a little strange to say. You're using the X component and the Z component to form a Y component. And again, it's just what a cross product is. That's how we're doing it. We're looking for things that are 90 degrees apart from each other. And if you have something on the x-axis and you have something on the y-axis, what is 90 degrees from both the x-axis and the y-axis? And the answer is the z-axis. So that's why we're doing it those ways, is that everything has to be 90 degrees apart. Okay, so we'll do plenty of examples on this when we go onto the board, and you can also look at other videos, you can look at your book. Tons of different ways of doing cross product. Back on angular momentum, the whole point of this lecture on angular momentum. It works the same way as angular force. It involves two vectors that result in the cross product. Okay, so if we think of momentum, which was P is equal to m times v, if we put it fully in angular terms, we get a new term for angular momentum, which is called L. Okay, so we have angular momentum, and then instead of mass, we're going to substitute I. Instead of v, we're going to substitute w. So you see how we do the substitution for all angular versus all linear. P is equal to mv turns into L is equal to I w. Okay. You can also look at it as L, angular momentum, is equal to r crossed p, the linear momentum, r crossed p. So this would be the switch between linear and angular, right, is a multiplication by r, but two vectors need to have a cross then. Visually, what is happening? Okay, so visually you have an object that is moving into a circle here. Okay, as it goes around and around, you'll see a velocity, and the velocity is linear, it's a straight line, and you have a radius. So normally you would find momentum by mass and velocity, and that's the direction of the momentum would be upward. Angular, however, has to be 90 degrees apart from each of these. So if you flip this and look on it from up top, you will have the radius and the velocity, and the only way to get 90 degrees between both radius and velocity is to go in the z-axis. So your angular momentum will always point upward. Okay, same direction as your angular velocity. Okay, so our v switching over L, W, you have this angular momentum up. Now there's a lot of fun things to do at home if you want to look at angular momentum, mainly the conservation of angular momentum. So conservation in angular momentum is conserved just like regular linear momentum if it's in an isolated system. Okay, so everything has to be in an isolated system. You can't have friction, you can't have those things taking place that steal energy away if you want it to be conserved. So just a quick recap, the energy of a system, if it does not change, if the change is equal to 0, that means there are no energy transfers across system boundaries that can't be regained, is what I'm getting at here. Okay, so energy can transfer from object to object, but no energy can transfer across the boundary, such as heat, friction, stuff like that can get out, that you cannot recover back. Okay. Momentum, if the change in momentum is 0, this is linear momentum, it means that the net external force on the system is 0, so you actually don't have a push or a pull going on to the system from an external force. It means all the forces are already in the system and they stay in the system, and all that's happening is a change in momentum which results in 0. So one object might give velocity to another object, but in turn it has to slow down itself, right? So like two pool balls or something. So we discussed this in the last chapter, so this should be pretty familiar. And then now we have the new angular momentum. Angular momentum, of course, same thing. Instead of force, it just means that there is no net external torque. So you cannot have an external angular force on the system. Okay, so same principles apply to linear momentum as angular momentum. You just cannot have any external force working on your system. If that is the case, right, where the total angular momentum comes out to be 0, then you can set it up just like any other conservation equation, where you would have I omega in the initial is equal to I omega in the final, which is just a constant number. Okay? It means that these aren't changing. Equal, 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 equal. It's all the same, which means if you're going to change momentum in one, it has to change something in the other, and usually it will be the moment of inertia that changes, that will give you the two different angular velocities. It's a very, very common problem that we'll do with those. This is actually how figure skaters get to spin so fast. They have a very high angular velocity when they are in midair twirling around. They can do numerous rotations in midair. Why is that? Well, they change their moment of inertia. They come from a system where the angular momentum is zero, everything is conserved, and you'll notice that when a figure skater goes in to do a twirl, okay, their arms and legs are usually spread out as far as possible, and then once they start to spin, they pull in really, really, really tight. They pull their arms and their legs in together, and that changes their moment of inertia. It lowers it considerably. So if you lower one of the moments of inertia, that means you have to have an increase in the other variable, which is the angular velocity. It's really cool how figure skaters are able to do that. And that's just one example. You can also do this at home with an office chair. If your chair has wheels and you're on a slick surface, like well, technically you wouldn't have to be on a slick surface, I guess. If you have a spinny chair, something that rotates, or a stool or something like that, if you put some weights in your hand, and they don't need to be very big weights, just a couple of pounds, laundry detergent, or even a minimal, you could do cans of soup or something. But ideally you'd like, maybe 3, 4, or 5 pounds each in your hands. Hold your arms out straight if you can, out to the sides, and then start to spin in your chair. And you can use a friend, or you can use your foot to get started spinning. But once you've got a little bit of a spin with these weights being all the way out, your arms completely outstretched, pull the weights in towards your chest and see what happens. You will increase your speed dramatically. To slow back down, you simply put the weights back out to slow back down, pull them in to speed up. It's a very unique effect. You're able to see it, and that's because there's no external torque added to you. You've given yourself a little bit of a head start by starting to spin, but after that you're not pushing yourself with your foot, so there's nothing else being added in, and just the change in the moment of inertia changes to a very large change in angular velocity. It's pretty cool. Anyway, let's see a couple of examples of these. So let me hop on over to YouTube. We'll watch a couple of videos. Alright, so we have one here of a cat. I don't know why it's partly cut off here, but a cat released upside down without any initial rotation lands on its feet. It turns itself by 180 degrees. There are no external torques acting on the animal. You can just see that it is simply rotating around its center of mass there. The total angular momentum is 0 all of the time, so there is no angular momentum that's happening. If we look at rotational, if we look at local axis, and we look at the center of mass, you see that they kind of remain the same there, and that angular momentum back and front can kind of just switch around and get the cat to position itself in a way. So it's pretty cool that a cat, this is why they usually land on their feet, is because it bends its bodies. It's basically becoming a cylindrically contracting on its torso. It's pretty interesting. Alright, second example. Again, if you want to see these whole videos, I'll put the links down below in the description. This is a gentleman here trying to hold this giant weight out with one hand by the end of the rod. And if you kind of imagine this in person, you'll see people struggle with it. It's very hard to do, to hold that weight out there. And the reason is everything's just linear at this point. You're acting like a pivot. You need to have a lot of force in order to to get that, to hold that up at that length. But if you spin it like they're doing here, we've got a drill that is spinning the weight, and you're adding a whole bunch of linear momentum to the weight. You can now see, when he lets go, you can now see that it wants to stay in place. Okay, which is pretty cool. It looks weightless, not quite, but it's getting there, close. Again, I can put some links to the descriptions of the videos below. It's a pretty cool little thing. Gyroscopic precession is the technical term. They can do it also with bicycle wheels. This is the reason why you don't fall down, or you have a harder time falling down on a motorcycle or a bicycle when you gain speed, is because that momentum keeps you upright. And if you've ever ridden a motorcycle or driven a motorcycle, you know that you actually don't turn very much on the handlebars. It's more or less of a lean, and that's what you're doing, is you're changing where your mass is located, and then that also acts with a torque force, and it will turn the bike for you. It's a very, very cool little thing that's you can see and use in everyday life if you have a bike or a motorcycle. All right, and then the last video here is actually I think it's a advertisement for a stabilizer on a boat. Inside of the stabilizer on a boat is a geosynchronous ball that'll move according to the waves that it looks at. And look at the difference between the two boats, one that's using a stabilizer versus one that is not. So let's see here, we'll create a wake with this boat, and you can see how this one remains stable, much more stable than this one over here. And it's because that's creating an angular momentum counteracting the waves, and it's conserved. It's keeping that angular momentum conserved. You can see here it's moving around. It's gyroscopic. It's called the Seakeeper, and it's pretty cool just by having this thing inside spinning and then rotating its axis to work against the waves. That's pretty cool. It's a pretty cool little device. All right, that's all I got for you on this lecture. Let's go to the whiteboard and we'll do out several other examples and practice problems and stuff.
Chapter 11, Example 1. In this one, we learned torque and angular momentum were cross products. So I do want to do a good cross product example here for you. Order of operations matter when you do these. So remember that when we convert from linear terms to angular terms, it's always r times something like theta or omega or alpha. It's the same in here as well when we take r multiplied by something, but these are in vector form. So it would be, for torque, it would be r crossed with the linear force, and that would get an angular force, which we know as torque. Same with angular momentum. You would take r crossed with a linear momentum, and that would get you torque. So order of operations does matter here. I have got the rest of the equation there for the other conversions. For angular momentum, linear being mv, this one then would look like I omega. For torque, you have r, f, change in r sine theta. You can also write it like that. You can also write it as I alpha if you want all angular terms for torque. But anyway, we'll worry about the cross product for example 1. That's what we want to mess with here. So I have these two vectors. It's a force that is given by 2I plus 3J, and it's applied to a rotating object at a rotatable object at a distance of r, which is negative I hat plus 2J hat. And it asks what is the torque. So these is definitely going to have to, this is going to have to be a cross product problem, because we're given it in vector form and we have to multiply those two vectors together to get our solution. And torque in itself is a vector because it is a force. Same with linear momentum. It is a vector, so it should have vector components to it. Okay, so I do these probably a little bit different than some other people. There's a lot of ways of doing them. I like to make tables, so I'm going to set it up as a table. Now, I have to put it in order, so I'm going to start with R being my vector, and then I'll put F down below it so that R gets first, and then it's F down below. Now, when I write out the vectors, I'm going to have an I component, a J component, and I'll put in a K component. Now, it's important that we still put in the K component because we live in a three-dimensional world, and these vectors all have to be 90 degrees off from each other, so we do have to include all three of those directions when we add in. And now what I would want to do is put in what the vector actually is. So if I look at R is a negative I hat, so we could write that as a -1 in the I hat column for R. So you can see how we're kind of building a table. It's 2 in the J, so I'll put a 2 for R in the J column, and there is no K, so I'll put a 0 in the K column. I do the same thing with F. It is 2I plus 3J plus 0K. Pretty much all methods are going to have you come up with this table. If you look online or you search in your book, there's also a way where you can cover specific parts and then multiply, do some cross multiplication, and you either add a plus or a minus sign depending on where you are, which column you're in, because one is positive and then negative, then positive, it flips back and forth. I find it to be a little confusing and a little bit hard to remember. And being it's called a cross product, I like to actually cross it out. So what I do is I continue my table, but I just repeat it. So I'm going to put another I hat, another J hat, another K hat, and I'm just going to rewrite these. So -1, 2, 0, 2, 3, 0. So they just repeat. You have an IJK, IJK. We have a -1, 2, 0, -1, 2, 0. So they just repeat twice. Okay? And there's a reason why I'm doing this, is that there's enough room. When you make a cross, if you were going to make the cross symbol, how would you draw it, right? So I'm betting most of you come down first, and then you go back. You make the X, right? This is your step 1. You go down that way, then you move your marker over, or pen or whatever, and you come up this way. And this is step 2. Okay. I'm guessing that's how most of you are going to make a cross. Down, up. Okay. That's what we're going to use to do our cross product. All right. In step 1, I started in the upper left corner and I went down to the right. So that's what I'm going to do here. I'm going to grab a different color. Okay. And let's start with step 1. Okay. So I'm going to start in the upper left corner with the I, and I'm going to come down. And I get a 2 and a 0, and it's a multiplication, so it's 2 times 0. Well, 2 times 0 would be 0 I, right? I times 2 times 0, 0 I do the same with the J. I get a 0 times 2. That means I get 0J. And I do it with the K. I need all 3. And for the K, I get a -1 times 3. So that gives me a -3K. Okay, hopefully that made all right sense. So we've got step 1 done for all 3 of our dimensions. You just need 3 dimensions. That's all we're working with, 3 dimensions. But now it's time to go back and do step 2. Step 2 says we start in the bottom left and we go up. So I'm going to start in the bottom left and I'm going to go up. And I get 2 times 2 times K. That gives me 4K. And then I get a 3, 0 times I. That gives me a 0I. And then I get a 0, -1J. And that'll give me a 0J. All right, so I've gone down with the red and I'm going back up with the orange, and that's my step 1 and my step 2. We go down, and then we go back up, and we get these two quantities. So there's my step 2. Here's my step 1. And now all we have to do is take step 1 minus step 2. Okay. Step 1 minus step 2. Now all I'm doing here is I'm just looking for like terms. I have 0i here minus 0i here. So we get 0i. I have a 0j here minus a 0j here. So I get a 0j. I have a negative 3k minus 4k. Negative 3 minus an additional 4 will give me a minus 7k. All right, and that's the cross product. What is the torque? Torque is minus 7 in the k direction. Okay. And that keeps torque as our vector. It gives it a direction, it gives it a magnitude, negative 7k. Now, cross products, because of that sine theta, always want things at 90 degrees. So it's not a surprise that it's in the k direction, because our two initial vectors were only in the I and the j, right? So if something is in the x and in the y, the only direction that is 90 degrees to both x and y is the z direction, which is the k hat direction. Okay? So you'll notice that if we have vectors that are only in two of the dimensions that you have, you will always have the cross product showing up in the third dimension. Okay, so this is the way we do a cross product, or the way I do a cross product. You can do it however you would like. I like this one because it's pretty straightforward, I think, and makes it simple. Nothing too hard to remember. But feel free, use it however you'd like. You would do the exact same example for any cross product, which you'll do a bit if you do in Physics 2. Same thing for linear momentum, R and P, whatever your momentum is, P. You would put it in, and you do the exact same steps. You always do it the exact same way, and that's how you do cross products. Okay. All right, hopefully that was a good intro to cross products. Okay, let's look at another one, example 2 here. We're back to our merry-go-round question, but we're going to do it a little more in depth this time. It's going to be a little bit more work because now we've learned a little bit about linear momentum and how that can change with our moment of inertia. So when we talked about it the first time, we did changes in moment of inertia. Now we'll see how that moment of inertia relates to linear or angular momentum. Angular momentum. So this is our new problem now. It's a little bit more involved. We have our merry-go-round. We're looking from the top view of our merry-go-round, going around in a circle. The merry-go-round itself is 100 kilograms and the radius is 2 meters. This is the before picture. We have a small child, 60 kilograms, on the very edge of the merry-go-round, and the merry-go-round is spinning at 2 radians per second. Then something changes. The child gets closer to the center of the merry-go-round. They change their distance to only 0.5 meters instead of the 2 meters all the way on the edge. How is that going to affect the speed of the merry-go-round? Or will it at all? Okay, so this is linear momentum. It is a change. You have a before, you have an after. Okay, so you would think of it as a linear momentum problem, because there's a before and an after picture, like a collision that's occurring, something changed inside. It's the same thing with angular momentum, right? Except for that whatever is rotating has changed. Something has been added, taken away, or moved, and that changes the angular momentum. Okay, so that's just how to spot these problems. So we're going to have to use angular momentum. And we said, okay, in all momentums, is it conserved or is it not? That's always our first question, is the momentum conserved? Well, we don't see any outside forces coming in. There isn't rocket boosters being activated on the merry-go-round, or friction or some kind of weird external force that is dealing with this merry-go-round. So we can say yes, that our momentum is conserved, which means that the change in momentum would be equal to 0. Okay, which means then that our final momentum is equal to our initial momentum. Okay, which means our final moment of inertia, our final angular velocity would be equal then to our initial moment of inertia and our initial velocity, all angular. Now, we'll have to see what we want to do with this one. So it's a little bit simpler, I think, than linear momentum, being that there's only one object. Okay. Well, there's actually multiple objects, but combined, they only have one moment of inertia. So we can kind of treat it as one. So we have to start piecing this together. I am looking for that, right? I am looking for the final angular speed of the wheel. So this is the variable I'm looking for. How about the I, the final moment of inertia? How can I figure that out? Well, we can use parallel axis theorem. Okay, we can use parallel axis theorem for this. So I'm going to grab I final, and I want to write it out as being both the merry-go-round itself plus the small child being added. Okay, that's what I want to use for the I final. So my I final here, I'm going to give myself plenty of room. I need to have the moment of inertia of the merry-go-round, which is a disk, which isn't given here in the problem, but if I ever did give you this on an exam, I would give that to you as 1/2 mr squared. I'm going to put it as capital M because it's the big wheel, and I'm going to put it as capital R since we have multiple R's going on. Let's change that to a capital R. All right, so this is the moment of inertia of just the merry-go-round itself. Now we need to add in a person that was added to it. So we will have plus, and then this one, we'll use that as little m and little r squared. All right, so this is the new moment of inertia final, and we are looking for omega f. We're looking for the final speed. All right, now let's look at moment of inertia initial. Well, it's going to be pretty similar. We're going to use parallel axis theorem, 1/2 mr squared, that's the merry-go-round, plus we have one person and they're at a radius. We can do this. And then that's multiplied by the initial velocity, angular velocity. All right, now we just got to start kind of plugging in and realizing what numbers to put where. Okay, they both look very similar, so we'll have to figure this one out. For the large M, that doesn't change whether it's final or initial, so I can go ahead and write that as 100. Okay, it's 100 kilograms for the wheel. The radius of the wheel, does that ever change? No. So I can put that as 2. Okay, it's the same in the final and the initial. The mass of the child, well, that's 60. It's given up here. Mass of the child doesn't change. But R sure will. So this is in the final. In the final, the radius or the distance that the child is away from the center is 0.5. So I want to make sure I get 0.5 in the right spot. All right, and then that whole thing is multiplied by omega f, the final. In the initial, it's very similar. We'll have 1/2, we have 100, we have 2, okay, because it's still the same mass of the merry-go-round, the same radius of the merry-go-round, same mass of the child, but its radius in the initial. The radius in the initial is the child all the way on the edge of the merry-go-round. So That would also be a 2 in this case, because the radius of the merry-go-round is 2. Child all the way on the edge would also be 2. Oh, and then omega I we actually have. Given in the problem there, it says that in the initial, omega I was 2 radians per second. Okay, so we can multiply that whole thing by 2. Okay, so this one isn't too bad. It's just a lot of plugging in and knowing what to plug in. But in reality, your calculator can handle all of that, right? So let's just see what I get here. And for the first one, we get, of course, this is 4. Half of 4 is 2, so 100. This would be 200. So we have 200 plus a quarter of 60 is 15. 215. 215 omega F. And then on the other side, we have, again, 200. But that one's 6 times 4, so another 240. So 440 times 2. All right, so if you plug in this whole number here, what I'm going off of is we have 200, we have 240, so that's 440. 440 times 2 is 880. All right, now we just need to divide 880 by the 215. That should give us omega F of, do you think it's going to be faster or slower by moving that to the center? If you guessed faster, that is correct. As I said in the video, if you have if you're in like a rotating chair, like an office chair, something like that, and you have weights, you can put those weights very far out and start spinning in the chair. Okay. When you have some rotational speed and you're spinning in the chair and you have your weights all the way out, bring those weights in, and you'll see your speed dramatically increase if everything is, if your chair is greased up and frictionless as much as you can and stuff. You'll see your speed speed up, which is exactly what we see here. We have child head more towards the center of the circle, and it speeds up speeds up over twice. Anyway, over twice as fast. All right, we'll go ahead, box that answer, and we'll move on to example 3. All right, let's try another one. Example 3 here. In this one, we have a star that's about to collapse. So here we have a before image of the star. The star has a radius of 10,000 kilometers, and it rotates with a period of 720 hours. So remember back to period, that is the amount of time it takes for one full rotation. So Earth's period is 24 hours to go around for a day. This one's more closer to 30 days to go around. Actually, it is 30 days for one full rotation. So it's a very slow spinning star. Okay, but something's going to happen to that star. The star's internals are collapsing on themselves. And what's going to happen is the entire star is going to give to gravity and collapse in on top of itself. And it will result in a much smaller, more dense star with the same mass, but only 3 kilometers for its radius. Very, very small star. And that big shift in mass is going to, of course, change its speed and, in effect, change its period. Okay. So these things are pretty cool, especially for like astrophysics, to look at stars collapse or to look at collapsed stars and regain back to what they once were, perhaps. Either way, we have a before, we have an after. So this should be a clear indication now that before and afters usually deal with momentum problems. Okay, what type of momentum? Well, it told it was a period and it was rotating and there's an I involved. So angular momentum is most likely where we want to go with this. Now, when we have momentum, we have to ask ourselves the question, is the momentum conserved? Is there any kind of outside forces that are affecting the star Is there anything resistive going on, like air resistance or anything? And no, none of that's apparent in the question, which means angular momentum is conserved, which means the change in L is going to be 0, which means LF is equal to Li, which means I omega F is equal to I omega I. Okay, finals and initials. The moment of inertia was given. It's still a sphere. It's a solid sphere in both cases, so there's only one moment of inertia. We're not adding anything to it. There's no extra masses to get added on, so the moment of inertia is simply what it is. 2/5 mr squared omega F is equal to 2/5 mr squared omega I. Okay. Now I've got a 2/5 in both sides of my equation here. I'm going to go ahead and just cancel those out. I don't need to worry about that. I also have an m on both sides of the equation. And the mass remains the same in the start. It's not losing any mass. So the mass in the beginning is the same as the mass in the end. So we can go ahead and cancel that out, which is good because it wasn't given in the problem. So what we have left here is r final squared, and in the end, it is 3 kilometers, which is 3,000 meters. Okay, so let's go 3,000 meters to get it in SI units, and then that'll be multiplied by omega F, which we'll need omega F for the period. How about on the initial side? We have the initial radius squared. Okay, well that was 10,000, but it's in kilometers, so to convert it to meters, we have 10 million meters squared, and its initial speed, omega I. Well, what is omega I? We were given a period, okay? So we could probably solve for omega I with that. If you remember back, we have period having an equation of 2 pi over v, so distance, 1 full revolution, distance over the speed, and that will give us a time. But we don't want v in here, we want omega, because it's angular, so we want to put an omega in. So we have the conversion to get it into omega. V is equal to Rw, so if we replace V with Rw, the R's up top will cancel, and we'll be left with a period as 2 pi over W. Okay. If the period is equal to 2 pi over W, I can use this period in that equation. I'll just have to have T is equal to 2 pi over Wi. So that's where I'm going to get my Wi from. But the period isn't in the right units, is it? So for period, I'm going to have to change that over to seconds. And it's going to be a bit 720 times 3,600 for every 1 hour, there's 3,600 seconds. If I'm going to change that over, do the conversion, make sure you know how to do them. It'd be 2,592,000 seconds. Okay, so this is hours, but in seconds. Okay. Now I need to solve for omega I. Well, that means I'm going to have to take 2 pi and divide it by that big answer. And it gives me a really small number. 2.42 times 10 to the negative 6th. Okay, really, really, really small number there. 2.42 times 10 to the negative 6. That's my omega I. All right, well, we got really big numbers over here, so that's okay if we add in a really small number. What happens here if we start plugging in some of these values? If we do 3,000 squared, that comes out to 9 million, or 9 times 10 to the 6th. If we do 10 million squared, Wow, calculator's just being super fun. I just wanted to get the scientific notation on it just to make sure I don't make any mistakes. It's 1 times 10 to the 14th, which is what I should have went with my gut. Anyway, 1 times 10 to the 14th times omega I. Now we found what omega I is. It's 2.42 times 10 to the negative 6. Okay, so we're getting omega I from over there, and these ones we're getting in. So the only thing that we have left to solve for is omega F. So let's multiply these out. Let's solve for omega F and see what we can get. So on this side of the equation, I'm going to get 242, 2,420,000,000. And then I need to divide by that large number of 9 times 10 to the 6th. So that should give me a nice, easy number of 26.9 rads per second. Hopefully that was right. 26.9 rads per second. Don't box the answer because that's not what the question was asking for. The question was asking for what is the period. So we have to plug back into the period. And we say, okay, well, t is equal to 2 pi divided by this number, 26.9. So what does the period equal? Do you think it'll be faster? Think it'll be slower? We will soon find out. All right, so now the period goes to 0.23. I'm just going to round. You might get something close to that. But now we are in the SI units of seconds, which means it does a full second in less than a quarter of a second. A full revolution in less than a quarter of a second. Sorry, it's early morning. Okay. It means 4 times this thing spin around every second. It's a very, very fast spinning star. Easily seen in the night sky, easily identifiable. Sometimes they even have jets or plumes that are coming off of them because they're spinning so dang fast. So very, very cool that we had a star that was very slow, 720 hours for one rotation, after collapse is in spinning incredibly fast. All right, cool. Hopefully that helped. And then in the next chapter, we talk about some space stuff. So I'm kind of introducing some space, some very large numbers here to get you used to that.